3 stars, spaced almost perfectly even, hang in a straight line above the horizon tonight. That line is the biggest optical illusion the night sky hands you for free. One of those 3 points of light isn't one star. It's a nested system, and astronomers didn't resolve the last piece of it until 1999. Still news to most people who've stared at that belt their whole lives. The 3 stars are drifting apart in 3 different directions, at 3 different speeds. The westernmost one is hiding 4 separate companions inside a single point of light. Babylonian astronomers were charting that exact line more than 3,000 years ago. And the truth about what it actually was took until 1999 to fully arrive. Tonight, we take that line apart, star by star. We'll stand inside the mistake a Paris astronomer named Deslandres made in 1900, and watch it become the discovery that mattered 5 days later. We'll meet the 5 stars hiding inside a single point of light. A1, A2, AB, B, and the 1 still argued about. By the end of tonight, you'll know exactly how many stars you've actually been looking at, your whole life. That easternmost star is Alnitak, and it isn't heat that lights the cloud beside it. It's ultraviolet light, tearing electrons off hydrogen atoms a few light years away. Let's begin. Picture the 3 stars the way you've always seen them. Evenly spaced, perfectly level, a short, straight cut across the middle of the hunter's shape. It looks deliberate. It looks assembled. Astronomers spent a long time treating it that way too. As if 3 stars sitting in a row had to mean something, had to be connected by more than the accident of 2 eyes looking up from one small planet. They don't. Move even a modest distance from Earth. Not across the galaxy, just far enough to change your angle by a few dozen light years. And the line breaks apart completely. The 3 stars scatter into a shape with no name and no symmetry. Nothing you'd bother sketching on a cave wall. The alignment you're looking at tonight is an accident of where you happen to be standing. And nowhere else in the universe is anyone seeing what you're seeing right now. Here's what those 3 points of light don't tell you just by looking at them. They aren't at the same distance. Not close. The westernmost star sits roughly 1,200 light years away. The eastern one sits about 1,260. And the star between them, the one that looks brightest and most central, sits so much farther back that astronomers still argue over exactly how far. Somewhere between 1,300 and 2,000 light years, a gap wide enough to fit hundreds of stars end to end between the near wall and the far one. Hold that number. Now, put your own body in it. If the belt were a hallway and you were standing at the doorway, the near wall would be close enough to touch, and the far wall would be lost somewhere past the point your eyes could still resolve it as a wall at all. What reads as a row of 3 objects standing together is really a straight shot down a corridor, and the only reason it looks like a line is that you happen to be standing at the one point in the galaxy where the walls overlap. 3 stars that have never once agreed to be a line. The depth isn't even the strangest part. These 3 stars are also moving, each one drifting through space on its own private heading, and not one of them is angling toward the other 2. In a few 100,000 years, an eye blink by the timescales the rest of tonight will use. The belt above your head will not exist in this shape again. The 3 points will have spread far enough apart that no one standing on this planet will draw a line through them anymore. Something you have never once doubted is quietly running out. That would be enough of a shock for one segment. Because the number 3 is about to stop being accurate tonight, in a way that has nothing to do with drift and nothing to do with distance. One of those 3 stars was never one star to begin with, and the last piece of that secret, the piece that took a century to nail down, didn't come from a telescope pointed at the sky. It came from a mistake made in Paris, in the first year of a new century, by a man who thought he had found something completely different. Somewhere around 1,000 years before the Common Era, Babylonian skywatchers catalogued this stretch of sky in a text now known as mul.apin, a working list of stars grouped by the season, each one rose just before dawn. The 3 belt stars appear in it as a single fixed marker, used to time planting seasons the way a modern calendar times a harvest. Centuries later, sailors from a dozen different cultures steered by the same 3 points, because a short straight line of stars is one of the easiest things a tired human eye can find in a crowded, moving sky. Not one of those navigators on any of those ships ever knew they were steering by a hallway rather than a wall. For most of human history, that never mattered. 3 stars don't need to be physically connected to be useful. They only need to hold still relative to each other for as long as a human lifetime. And on that timescale, they do. A sailor crossing the Mediterranean 2,000 years ago and a sailor crossing the Pacific 2 centuries ago were, for all practical purposes, steering by the exact same 3 points of light. The illusion was stable enough to build entire trade routes on top of it. Stable enough that nobody had a reason to doubt it. But stability was never the same thing as truth, and that gap is where the rest of tonight actually lives. The 3 stars felt permanent because nothing available to the naked eye. Not 1 lifetime, not 100 lifetimes, stacked end to end, moved fast enough to reveal the drift underneath. It took instruments, not eyes, to catch 3 stars in the act of leaving one another. And once astronomers finally pointed the right instrument at the belt, closely enough and long enough, they didn't just confirm the drift. They found something sitting inside one of the 3 points of light that had nothing to do with distance or direction or any of it. That discovery didn't start with someone looking for a hidden star. It started with someone trying to measure something far simpler. The speed of a single point of light, moving toward and away from Earth, and getting a number that refused to make sense. Nobody sets out to find a 5-star system hiding inside a naked eye point of light. That kind of discovery only ever arrives sideways, as a byproduct of someone doing a much smaller, much less glamorous job carefully enough to notice the job wasn't behaving the way it was supposed to. Every layer of tonight's central mystery. The eclipsing pair, the hidden companion, the 2 still argued about stragglers, starts from exactly that same unglamorous place. A measurement that should have been routine, and wasn't. Repeated night after night by someone with no idea yet what they'd eventually stumbled into, or how long it would take anyone to believe them. Orion's belt is a single name for 3 objects that have nothing in common except the accident of your line of sight. Take that name away, and what's left are 3 unrelated blue giants, each with its own biography, each with its own mass, each with its own way of eventually causing trouble for the tidy little row they seem to belong to. Whether they share anything deeper than appearance, a birthday, a birthplace, an actual family tree, is a question tonight is going to answer properly later, and not in the way a first glance would guess. For now, treat them as 3 actors cast for a single role purely because they looked right standing next to each other, with no director ever actually arranging the scene. The middle star is the one nobody can pin down. It isn't the faintest of the 3. It's actually the brightest in real terms, radiating more raw energy than either of its neighbors. It's hard to measure not because the telescope struggles to see it, but because the star itself won't hold still. It's shedding material into space so fast and so violently that different measurement techniques return different distances for the exact same point of light. Astronomers have argued about how far away it actually sits for decades, and the argument still isn't settled. The eastern star is the one doing something to its surroundings. It isn't just sitting in the dark, it's actively lighting a nearby cloud of gas on fire. In the sense that matters to a physicist, stripping electrons off hydrogen atoms with raw ultraviolet output, turning a patch of otherwise invisible interstellar dust into one of the most photographed objects in the night sky. And it's carrying a second star tucked so close beside it that for most of the 20th century, nobody could prove it was there at all. The western star is the one keeping the real secret, not because it's the faintest, and not because it's the most distant. It's roughly the closest of the 3, It's the one hiding 4 separate companions inside a single unresolved point of light, discovered in pieces over the better part of a century by 4 different methods that each caught a different member of the family and had no idea at the time that the others existed. 3 names, 3 completely different stories. And not one of them is really about a belt at all. Notice, too, what these 3 stories share underneath their differences. Every one of them is a story about something hidden behind a simpler appearance. A star, too restless to measure honestly. A star with an invisible partner tucked inside its glare. A star wearing 4 extra faces nobody could see for a century. The belt's real subject was never the line connecting these 3 points. It's the gap between what a glance shows you and what a closer, more patient look eventually reveals. A gap that turns out to be the actual through line of everything left to cover tonight, from here all the way to the last segment before sleep. Every star in the sky has what astronomers call proper motion, a real, measurable drift across the sky, on top of its motion toward or away from Earth. For most stars, that drift is too slow to notice across a human lifetime, but it isn't zero, and it doesn't stop, and over long enough timescales it redraws every constellation currently in use. 50,000 years is the number astronomers usually reach for when they want to describe how long it takes proper motion to visibly wreck a familiar shape. It sounds enormous. Against the 13 billion year age of the universe, it's closer to a single held breath. And the 3 stars of the belt are drifting fast enough, in different enough directions, that 50,000 years is roughly the scale on which the straight line you're looking at tonight stops reading as straight to a naked human eye. Nobody alive will see it happen. Nobody's grandchildren will see it happen. But it is already happening. Right now, while you listen to this sentence, all 3 stars are measurably farther from forming a straight line than they were the moment you pressed play. The drift isn't a future event. It's a current one, just too slow for a human nervous system to register directly. And yet, every culture that ever named this shape treated it as fixed. A landmark, not a passenger. Farmers set their calendars by it. Sailors set their heading by it. Nobody built a myth around 3 stars slowly walking away from each other, because nobody could see them do it. The permanence was never in the stars. It was in how briefly any single human gets to watch them. So tonight isn't really a story about whether this belt survives. It doesn't. Not in the shape you know it. What's left to tell is everything hiding inside it before that happens. The 5-star secret at one end, the fire-breathing giant at the other, and the lone, distant star in the middle that still won't tell anyone exactly how far away it stands. None of that urgency is meant to rush you. 50,000 years is not a deadline in any sense that should sit uneasily tonight. It's simply the honest backdrop against which everything else makes a little more sense. A shape this temporary was never going to hold still forever. And knowing that doesn't make it less worth looking at tonight. If anything, it's the opposite. A shape this fragile, held together by nothing but coincidence, and about to unravel on a clock longer than any species has existed, is exactly the kind of thing worth a full hour of unhurried attention before it changes into something else entirely. If this is the kind of night you return to, subscribe. It helps this quiet universe keep growing. We start in the middle of the line, with the star that refuses to be pinned down. Alnilam is the brightest true light source in the belt. Not the brightest as seen from Earth, but the brightest in the sense that actually matters. The amount of energy leaving its surface every second. Pour that output through the same distance as its 2 neighbours, and it would outshine both of them combined. It is a supergiant in the most literal sense the word allows. A star bloated to roughly 20 times the width our Sun would need to touch Mercury's orbit, burning through its fuel so fast that its entire visible life will be measured in a few million years, not billions. And astronomers still can't agree on how far away it is. Not because nobody's tried. The Hipparcos satellite measured its position precisely enough back in 1997 to produce a distance estimate, and later reanalyses, using the same raw data with improved methods, produced a different number. Ground-based techniques disagree with satellite techniques. Different teams publish figures that range from around 1,300 light-years to nearly 2,000, and the gap between those two numbers isn't a rounding error. It's roughly the width of 700 light-years. A distance longer than the star is far from many of its closer neighbors, sitting inside a single supposedly solved measurement. Here's the part that makes it worse. Distance isn't a side detail for a star like this. It's the number every other number depends on. Get the distance wrong, and you get the true brightness wrong. Get the brightness wrong, and you get the mass wrong. Get the mass wrong, and every estimate of how this star will end its life, how much longer it has, how violently it goes, inherits that same uncertainty. Astronomers aren't unsure about a footnote. They're unsure about the ruler the entire biography is written against. Part of the reason is the star itself. Alnilam isn't a stable point of light holding still for measurement. It's actively throwing material off its own surface, in a wind moving at roughly 2,000 kilometers a second, fast enough to cross the distance from Earth to the Moon in 3 minutes, carrying away the equivalent of 2/millionths of the Sun's entire mass every single year. That sounds small until you compare it to our own star. It's on the order of 20 million times faster mass loss than the wind coming off the Sun right now. A supergiant like this isn't just large, it's actively unraveling in real time. And the same instability that makes it worth studying is part of what makes it so hard to pin down. Parallax, the technique underneath most of this, works by watching a star shift very slightly against the background sky as Earth swings from one side of its orbit to the other. The same trick your own eyes use to judge how far away something sits, just stretched across a baseline nearly 200 million kilometers wide. For a nearby star, that shift is easy to catch. For a star as far and as restless as Alnilam, the shift is a fraction of an arcsecond. Smaller than the width of a coin, held up and viewed from hundreds of kilometers away. And it has to be extracted from light that the star itself keeps contaminating with its own outflowing wind. So the middle star of the belt keeps its exact distance to itself. But it isn't quiet about its future. Every second, Alnilam sheds enough material into space to plate a small planet in stellar dust. And it has been doing this for its entire short life, which by stellar standards has barely started and is already most of the way finished. Stars this large don't get long. The same mass that makes a supergiant brilliant is what burns through its nuclear fuel at a reckless pace. And Alnilam has nowhere near the billions of years an ordinary star gets to work with. Not because it made some early mistake, because mass is the whole story. From the very first moment of ignition, a star roughly 40 times heavier than the Sun burns through hydrogen, then helium, then a stack of progressively heavier elements, each stage faster than the last, until the core is producing iron, the one element that gives nothing back when it fuses. That is the moment the star stops being able to hold itself up against its own gravity. Every layer above the core has spent millions of years pushing outward against that same gravity, and the balance holds only as long as the fusion underneath keeps producing energy to lean on. Hold that number, iron, when a star like Alnilam finally reaches an iron core. The collapse that follows takes a fraction of a second. The explosion that follows the collapse is bright enough to briefly outshine every other star in its home galaxy combined, visible in daylight from thousands of light years away for the small handful of days it takes to fade. That hasn't happened yet. Best estimates put the event somewhere in the next few 100,000 to roughly 1,000,000 years. Soon, on any clock except a human one, and when it does happen, the star will already be gone by the time anyone on Earth sees it. Light takes over 1,000 years to cross the distance between here and there, so the flash you'd eventually see marks a death that occurred long before the light left the star's surface. There's a detail almost nobody mentions when they describe a supernova. The light isn't actually first. Hours before any visible flash, a collapsing core like this one releases a flood of nearly massless particles called neutrinos. So many, in such a short window, that in 1987, when a star inside a neighboring galaxy went through this exact process, detectors buried in mines on opposite sides of Earth caught a handful of them arriving before any telescope on the planet saw a single photon of light. When Alnilam finally goes, whatever happens to be watching from nearby will register that flood of particles first. The light is the announcement. The neutrinos are the event actually happening. This is not a controversial prediction. It is one of the more confident things astronomers say about any single star in this belt. More confident, ironically, than the distance measurement it depends on. The ending is not in doubt. Only the ruler used to describe it is. Compare Alnilam to its two neighbours, and one detail stands out immediately. It appears to be alone. Alnitak is a crowd of at least 3 stars orbiting a shared centre. Mintaka, as tonight will spend a great deal of time proving, is closer to a small cluster than a single point of light. Alnilam, as far as any survey has managed to determine, is just one star. No eclipsing companion, no resolved binary, no faint neighbour caught hiding in its glare. That could mean it never had one. Massive stars often form in tight groups, but not always in tight pairs. Some are born solitary from the start, condensing out of their birth cloud, with no sibling close enough to fall into orbit. It could also mean a companion existed once and simply isn't there anymore, merged, ejected, or stripped away long before any instrument on Earth was built to notice. Both explanations are on the table. Neither one is settled. There's a kind of loneliness in that. If you're willing to sit with it for a moment, 3 stars sharing one accidental line across the sky, 2 of them crowded with family, and the brightest one of all standing in the middle without another star close enough to call its own. It didn't choose that. Stars don't choose anything. But the shape of it, alone in the middle, flanked on both sides by systems with company, is the kind of detail that would feel deliberate if you didn't already know better. It isn't deliberate. It's just how this particular cloud of gas happened to collapse 4 to 6 million years ago, in the same stellar nursery that eventually produced all 3 belt stars and thousands of others besides. Alone and unrelated are not quite the same word, and the difference between them is about to matter. Alone also turns out to mean something else here, something closer to invisible. Every image of Alnilam you've ever seen, in a documentary, a planetarium show, a textbook diagram, is an illustration, not a photograph. No telescope currently operating on Earth or in orbit has ever resolved the star's actual disk. At its distance, even a giant tens of millions of kilometers across shrinks to a single point of light, too small for any existing instrument to render as more than a dot with spikes drawn around it by the imaging software. What we know about its surface comes entirely from spectroscopy. Light broken into its component wavelengths, read for the fingerprints of specific elements, specific temperatures, specific velocities. Astronomers can tell you what Alnilam's outer layers are made of, how fast its wind is moving, how its brightness flickers over days and weeks, all without ever seeing a single feature on its surface directly. It's a full biography, written from a light source with no visible face. That gap between knowing and seeing is easy to miss, because the pictures fill in the blank so convincingly. But it's worth sitting with once. Everything in this segment, everything about mass and wind speed and fuel and fate, was reconstructed from a point of light so small and so far away that no camera built by humans has ever seen it as anything more than a single, dimensionless pixel. Not gradual, not partial. Every image of that surface you've ever looked at was drawn by a person, not captured by a lens. The neighbouring star, on the other hand, isn't nearly so shy about what it's doing to the space around it, because part of what it's doing is visible from Earth with nothing more than a backyard telescope and a clear night. Alnitak looks, at first glance, like the most straightforward member of the belt. One bright point, catalogued, classified, done. It is in fact the opposite. A blue supergiant, roughly 28 times heavier than the Sun, with a second star locked so close beside it that no telescope has ever separated them visually, and a third star further out that takes 15 centuries to complete a single lap. Now add one more layer most descriptions leave out entirely. Massive stars like Alnitak's primary are, almost without exception, non-magnetic. Their interiors churn too violently, too chaotically, to organize into the kind of stable magnetic field smaller stars like the Sun maintain with ease. Out of the thousands of hot, massive stars catalogued across the galaxy, only a small handful have ever been confirmed to carry an actual, organized magnetic field, and Alnitak's primary is one of them. Astronomers found it using spectropolarimetry, splitting a star's light not just by wavelength, the way ordinary spectroscopy does, but by the orientation of its polarization. A signature a magnetic field imprints on light passing through it in a pattern no other stellar process reliably produces. The field itself is faint by planetary standards, weaker than a refrigerator magnet, spread across a star 20 times the width of the Sunday. But at that scale, faint is not the same thing as small. It's strong enough to shape the star's own outflowing wind, channeling material along field lines instead of letting it escape evenly in every direction. You've likely seen a small-scale version of exactly this mechanism without knowing it. Earth's own magnetic field does the same job at a fraction of the size, catching charged particles streaming off the Sun and funneling them down toward the poles, where they collide with the atmosphere and bloom into the aurora. Alnitak's field performs the identical trick, trapping and redirecting a stream of outflowing particles, except the wind it's shaping could, at the right distance, swallow the entire solar system whole, and the funnel it creates is wide enough to leave visible fingerprints in the star's spectrum from 1,200 light-years away. Nobody fully knows why this particular star kept a field that almost every star its size has long since lost. One idea: it may be the leftover product of a stellar merger earlier in its life, two smaller stars combining into one and briefly generating a magnetic field in the violence of the collision, a field that has been slowly fading ever since, and that Alnitak may simply be caught in the act of losing. It's a real hypothesis, not a settled answer, and it will not be settled tonight. What is settled is rarer than the mystery itself. Among every hot, massive star catalogued in this part of the galaxy, this one is still one of only a small number confirmed to be carrying an organized field at all. The second star in this system, the one riding close enough to blur into a single point of light with the first, has never been resolved directly by any telescope, ever. Not Hubble, not any ground-based instrument, however large its mirror. What astronomers know about it comes entirely from the way it tugs the light of its brighter neighbor back and forth. A rhythmic wobble precise enough to reconstruct an orbit nobody has actually seen with their own eyes. That orbit takes 2,687 days to complete. Just over 7 years. And it isn't a tidy circle. The two stars swing from close to closer and back again on a stretched, lopsided path, tracing an ellipse with almost exactly a third more stretch to it than Earth's own nearly circular orbit around the Sunday. 7 years. Invisible the entire time, confirmed only by the wobble it leaves behind in someone else's light. This is the same basic trick astronomers use to catch hidden planets around other stars, just tuned for a much heavier, much faster partner. A star moving toward Earth compresses its own light to slightly shorter wavelengths. A star moving away stretches it longer. Neither shift is visible to the eye, but a spectrograph reads it precisely, and a companion too faint or too close to ever photograph gives itself away purely through the rhythm of that back and forth stretch and squeeze. It's a technique built entirely on the idea that you don't have to see something to prove, beyond reasonable doubt, that it's there. Now layer the third star on top of that. Alnitak B sits far enough out to be seen directly, faint but real, orbiting the inner pair on a lap that takes roughly 1,500 years, long enough that not one measurement of its full orbit exists anywhere in the historical record. Every estimate of that period is extrapolated from a small arc of motion, a few centuries worth of nudging, projected forward and backward across a timescale longer than most written civilizations have survived. So, one star you can see but never separate from its neighbor. One star you've never seen at all, known only by the way it moves something else. And one star with an orbit so long that no human institution has existed continuously long enough to watch it complete a single lap. Three very different kinds of invisible, standing in for a single point of light your eye reads as one simple star. None of that invisibility is a failure of technology. It's a description of scale. A telescope that could visually split the inner pair would need to resolve detail thousands of times finer than the best instruments currently flying, because the physical separation between those two stars at this distance works out to a fraction of a single pixel on even the sharpest camera humanity has ever pointed at deep space. The wobble in the light was never a workaround. For a pair this close, it is the only method that could ever have worked. Here's what most people completely misunderstand about the glowing nebula sitting right beside this star. It isn't burning in any literal sense, and the far more famous shape nearby, the dark silhouette shaped like a horse's head, printed on more posters and screensavers than almost any other object in the sky, isn't lit up by this star at all. That backdrop belongs to a completely different star, well outside the belt. Alnitak is doing something else, right next door, and it rarely gets the credit. The cloud Alnitak actually powers is called the Flame Nebula, and the mechanism is pure ultraviolet violence. Alnitak's surface, hot enough to blaze blue-white instead of the sun's yellow, floods the surrounding hydrogen gas with radiation energetic enough to strip electrons clean off their atoms. Stripped atoms don't stay that way. They recapture electrons almost immediately, and every recapture releases a small burst of light at a very specific, very recognizable wavelength. Multiply that by trillions of hydrogen atoms across a cloud light years wide, and the whole structure glows on its own, powered entirely by one star's radiation. No combustion involved anywhere in the process. Not slightly wrong then? Completely wrong. If you've ever heard someone say Alnitak sets the horse head on fire, Alnitak lights a different cloud, by a different mechanism, standing in for a coincidence of appearance that has confused stargazers for as long as both objects have been photographed side by side in the same frame. What Alnitak is actually doing to its own cloud is, if anything, stranger than the myth. It isn't warming the gas, it's tearing it apart at the atomic level and lighting the wreckage. One star, alone, powering a structure light years across, entirely with its own restless surface. Most of that wreckage is invisible from the ground. Thick lanes of dust sit in front of large parts of the Flame Nebula, swallowing the visible light before it ever reaches a telescope on Earth. What finally let astronomers see through that dust wasn't a bigger mirror pointed at ordinary light. It was infrared observation, wavelengths long enough to slip past the dust that blocks everything shorter. The nebula astrophotographers show off in bright orange and gold is, underneath the color grading, mostly a structure that only became fully visible once instruments learned to stop looking for light and start looking for heat. A reminder that most of what this belt is doing, quietly, happens in wavelengths no human eye was ever built to register. We now know how the middle star and the eastern star each spend their violence, one unraveling itself into space, one lighting a nebula on fire from the inside. That leaves one star left to open, the one at the western end of the line, the one that has been waiting this entire episode, and it is about to turn out to be the strangest of the three by a wide margin. Mintaka is the westernmost star of the belt, the closest of the three at roughly 1,200 light-years, and for as long as it has had a name, it has been treated the same way its neighbors are, as one object, one entry in one catalogue, one point of light with one story. That treatment was wrong before anyone alive today was born, and it has taken the better part of a century to prove exactly how wrong. Here is the first layer, the one that's been confirmed the longest. What you call Mintaka is at minimum 2 stars locked in a tight orbital embrace, so close together that they complete a full lap around each other in less than 6 days. A third star, farther out but still gravitationally bound to the pair, takes centuries to complete its own orbit. That's 3. Inside a single point of light, already double what a naked eye, or a casual glance through a small telescope, could ever suggest. But 3 was never the final number, and this is where the deck gets bigger instead of smaller. Beyond that inner trio sit 2 more points of light, catalogued separately, sitting close enough in the sky and roughly consistent enough in distance that most descriptions now count the full system at 5. 2 of those 5, though, are held to a lower standard of proof than the other 3, spotted nearby, moving in a roughly compatible direction, but not yet nailed down with the same certainty as the tight inner orbit. Picture what resolving 5 separate points of light packed into one actually demands. The full spread of the system, edge to edge, covers a slice of sky smaller than a single arc minute, roughly the apparent width of a coin held at arm's length. Viewed from across a football field, inside that sliver, 5 distinct light sources are stacked at different depths and different brightnesses, and untangling them required 4 completely different techniques, developed decades apart, each one only capable of catching a piece the others had missed. No single method, no single year, no single instrument ever saw the whole structure at once, which means the real headline isn't "One star turned out to be 5. It's stranger than that. The number of stars hiding inside that single point of light depends entirely on how confident you require yourself to be before you're willing to say a star belongs to a family. Count only what's proven beyond reasonable doubt, and you get 3. Count everything that's probably real, and you get 5. Somewhere between those 2 numbers sits the actual, unresolved answer, and it's the kind of answer that resists the tidy summary most documentaries reach for. Tonight is going to walk through exactly how each of those pieces was found in the order scientists actually found them, starting with a mistake nobody was trying to make. In the year 1900, at the Paris Observatory, an astronomer named Henri Deslandres pointed his spectrograph at Mintaka and did something that sounds almost mundane. He measured how fast the star's light was shifting toward and away from Earth, night after night. He wasn't hunting for a hidden companion. He was doing the kind of careful, repetitive measurement that fills most of a working astronomer's career. The unglamorous foundation underneath every dramatic discovery that gets remembered later. The tools available to him were nothing like a modern instrument. A spectrograph in 1900 recorded its data on glass photographic plates, exposed for long stretches of a single night just to gather enough light from one star. Developed by hand, then measured under a microscope against a set of reference wavelengths etched onto the same plate. Every velocity Deslandres reported was the product of that entire chain holding together correctly. Chemistry, optics, and a steady human hand, repeated night after night, for a star that gave no outward sign it was hiding anything at all. What he found was a star whose velocity wouldn't hold still. Mintaka's light kept shifting back and forth in a repeating rhythm, the unmistakable signature of a star being tugged by something orbiting close beside it. Deslandres worked out a period for that rhythm. 1.92 days, just under 2 full days for the whole cycle. He published it, and it was wrong. 4 years later, a German astronomer named Johannes Hartmann went back over the same star with more data and found the actual period wasn't 2 days at all. It was 5.7 days, nearly 3 times longer than Deslandres had calculated, a correction significant enough to completely rewrite the physical picture of what the orbit had to look like. Not a small footnote in the margins, a number that had to nearly triple before anyone had it right. Here's what makes that mistake worth remembering. Instead of forgetting, Deslandres wasn't sloppy. Early spectroscopic measurements were genuinely difficult, gathered from photographic plates exposed for hours, read by eye, compared against reference lines by hand. Getting a repeating signal roughly right, in 1900, with the tools 1900 actually had, was already a real achievement. Getting the exact period right took 4 more years. A different observatory, and a second astronomer willing to question the first number instead of simply repeating it. That 5.7-day rhythm turned out to belong to the innermost pair of stars in the entire 5-star system, the tightest, fastest, most extreme orbit of the bunch, discovered first, correctly measured second, and still, more than a century later, the best understood piece of the whole hidden structure. Everything else this segment's neighbours will describe tonight, the third star, the fourth, the fifth, was found later, by other people, using tools Deslandres never had access to, chasing the same single point of light for entirely different reasons. That 5.7-day rhythm isn't just a velocity signal. It's an eclipse, the closest, fastest, most extreme kind of eclipse 2 massive stars can perform on each other, repeating every few days, completely invisible to the naked eye and only barely detectable, even with careful instruments. Here's what's actually happening at the center of that single point of light. 2 enormous stars, one larger than the other, orbit so close together that their separation is a small multiple of their own diameters. Nothing like the vast gap between Earth and the Sun, more like 2 objects nearly grazing each other on every single pass. From Earth's exact viewing angle, their orbital plane happens to line up almost perfectly edge-on, which means every 5.7 days, the smaller star passes in front of the larger one, and then, half an orbit later, disappears behind it. Each pass dims the total light by a measurable, repeatable amount. Not enough for your eye to register directly, even under a perfect night sky, but more than enough for a sensitive light meter pointed at the star over days and weeks to catch the pattern. This makes the inner pair what astronomers call an eclipsing binary, a system where geometry, not just gravity, hands you a way to measure it. That edge-on alignment is not the default. Most binary stars orbit at some random tilt relative to Earth, which means most eclipsing pairs in the galaxy never eclipse anything from our exact point of view. The geometry simply doesn't line up, and the system reveals itself only through velocity shifts, never through dimming. Mintaka's inner pair happens to sit close enough to that narrow edge-on window that the eclipse is real and repeatable, which is part of why this particular system became so useful to astronomers. It is one of a comparatively small number of massive eclipsing binaries, where the universe handed observers the easy version of the problem. Ask any astronomer studying stellar masses which single object taught them the most per hour of observing time, and a system like this one is a very common answer. From the depth and timing of those dips, and from the velocity data Deslandres and Hartmann were already gathering, astronomers could work out both stars' masses, both their sizes, and the exact tilt of the orbit. An entire physical portrait, extracted from nothing but a flickering point of light and the rhythm of its dimming. This particular pair holds a specific distinction worth sitting with. Among every eclipsing binary system made of genuinely massive stars, this is the closest one to Earth. Every star cluster in the galaxy almost certainly contains others like it, tucked into single points of light exactly the way this one was, still uncounted, still waiting for someone to notice a velocity that won't hold still. This one only stopped being invisible because 2 astronomers, 4 years apart, cared enough about a number that didn't quite fit to keep measuring it. The eclipsing pair accounts for 2 of the 5. A third star, orbiting that inner pair from much farther out, took a different kind of proof entirely, and it took 80 years longer to arrive. In 1980, an astronomer named Wolf Heinz identified a faint point of light sitting extremely close to Mintaka in the sky. Separated by roughly a quarter of an arcsecond, a gap so small it sits right at the very edge of what ground-based telescopes of that era could reliably distinguish from noise. Heinz proposed it as a genuine companion, gravitationally bound, not a background star that simply happened to align. The claim was plausible. It was also, for almost 2 decades, difficult to confirm beyond doubt, because separating 2 points of light that close together demands exactly the kind of resolution that atmospheric blur makes hard to trust. Confirmation, when it finally came, arrived from 2 completely independent directions at once, 19 long years later. In 1999, a team led by Brian Mason used speckle interferometry, a technique that takes thousands of very short exposures of a target, short enough to freeze the atmosphere's blur in each individual frame, then combines them computationally into an image sharper than any single long exposure could ever be, and resolved the companion cleanly, matching Heinz's original position. Separately, the Hippocos satellite, flying above the atmosphere entirely and free of the blur that limits ground-based instruments, had already caught independent evidence of the same companion in its astrometric data from years earlier. Hipparcos itself had launched in 1989 with a single, almost stubbornly simple mission: measure the precise position of more than 100,000 stars, repeatedly, over several years, and use the tiny shifts in those positions to build the most accurate star catalogue ever produced up to that point. Mintaka's hidden third star was never the mission's target. It was a byproduct, a companion, 2 independent projects each found, without particularly looking for it, each one arriving at the same faint point of light from a completely different direction and a completely different reason for looking in the first place. 2 completely different methods, one from the ground and one from orbit, converging on the same faint point of light. That's the third star, a subgiant orbiting the inner eclipsing pair on a path so wide it takes something on the order of 4 centuries to complete a single lap, discovered by inference in 1980, and not fully trusted until technology caught up with the claim 19 years later. 3 stars, now proven beyond reasonable doubt, spanning 80 years, 2 ground-based techniques, and 1 satellite that was never built to look for exactly this: a subgiant, an eclipsing pair, and the patient argument that finally tied all 3 together into a single, confirmed structure. 2 more remain, and this is where the story stops being a clean discovery and starts being an argument that hasn't fully ended. The 4th and 5th points of light sit much farther out than the first 3, far enough that companion starts to feel like the wrong word, and neighbour might be more honest. One is a faint 14th magnitude star, thousands of times dimmer than Mintaka itself. The other, catalogued separately under its own designation, is bright enough to see in a modest telescope, but still faint compared to the inner system, sitting at a wider separation still. Here's the actual disagreement, and it's worth stating plainly instead of smoothing over. Astronomers aren't fully certain either of these outer 2 is gravitationally bound to the inner 3 at all. They could be genuine members of the same system, drifting together through space on truly shared trajectories. Or they could be optical companions, stars that simply happen to sit in almost the same direction as seen from Earth, at a similar enough distance to look connected, without ever actually orbiting anything in this system. Distinguishing those 2 possibilities requires exactly the kind of long baseline motion tracking that takes decades to accumulate enough data to trust. The same patient, unglamorous measurement that eventually cracked open the inner pair, just aimed at a target so faint and so far out that the decades required haven't finished passing yet. So when this episode's title says one of the 3 belt stars is actually 5, that number is doing something a little more complicated than simple counting. 3 components are proven, gravitationally bound, beyond reasonable dispute. A 4th and 5th are catalogued, likely, cited by most serious sources, and still, technically, waiting on the kind of confirmation the inner 3 already received. That should feel uncomfortable, genuinely. and it's worth not smoothing that discomfort away. A number as basic as how many stars are in this system turns out to depend on how strict you're willing to be about the word belongs, which raises the real question sitting underneath everything covered so far tonight. If 3 stars sharing one accidental line across the sky were never actually one thing, and if 5 stars crammed into one point of light can't even agree among themselves on the word belongs, what was one star ever supposed to mean in the first place? Tonight will not hand you a clean answer to that question, and it isn't going to pretend otherwise. Human beings are built to see single things: one point of light, one star, one name, one shape, because that's the resolution our eyes and our attention were built to work at, and it has always been enough to navigate by, even when it wasn't quite enough to be true. The universe was never obligated to match that resolution. It doesn't here, and the honest response isn't to force a tidy number onto Mintaka. It's to sit inside the discomfort of a system that refuses to say definitively how many things it actually is. 3 stars that have never once agreed to share a distance. Here is the thread every fact so far has been quietly leading toward. The 3 belt stars are not connected now, and they were never one line in any physical sense. But they are not strangers either. All 3, along with thousands of other hot, massive stars scattered across this part of the sky, were born from the same enormous cloud of collapsing gas, in the same rough era as members of what astronomers call the Orion OB Association. OB refers to the type of stars the group is named for: hot, blue-white, short-lived giants, the same category Alnitak, Alnilam, and Mintaka's inner stars all belong to. An association isn't a tight, permanently bound cluster like a globular cluster, held together by gravity for billions of years. It's looser than that from the very start, a sprawling nursery of newborn stars, spread across hundreds of light years, sharing a birthplace and a rough birth date without ever being locked into a single shared orbit around a common center. That shared birth date sits somewhere in the range of several million years ago. Young, by any stellar standard, younger than almost every star visible to the naked eye on a typical night. For massive, fast-burning stars like these, several million years isn't early adolescence. It's already a significant fraction of a total lifespan that was never going to stretch past a few million years more. Put that number beside something you can actually hold in your head. The entire span of anatomically modern humans existing on Earth covers something on the order of 300,000 years. The belt stars are, conservatively, more than 10 times older than our species. And they were already approaching the end of their story before the first human ancestor stood upright. Their birth cloud has been gone almost that entire time. Only the light and the drift are still arriving. So the honest answer to are the belt stars related is neither of the two answers you'd expect. Not no, they're just an optical accident. They share real, traceable ancestry, born from the same collapsing cloud. And not, yes, they're a bound family, orbiting some shared center, because nothing has held that family together since the moment they were born. What connects them isn't gravity. It's a birth certificate, written in chemistry and velocity, that no amount of drifting apart can erase. Astronomers have gone looking for other members of that same birth cluster scattered even farther across the sky, stars that share the right chemical fingerprint and the right shared motion through space, even though they no longer sit anywhere near the belt itself. The Orion complex, in its broadest definition, stretches across an enormous swath of sky, thousands of stars strong, most of them never given a name at all. The belt stars aren't the whole family. They're just the three siblings bright enough and coincidentally aligned enough for one small planet to have noticed and drawn a line through. Here's how a birth cluster like this one comes apart. And it happens faster and more violently than most descriptions of stellar nurseries let on. A giant cloud of gas, hundreds of light years across, begins to collapse under its own gravity. Dense knots within it collapse faster still, each one contracting toward a single point until nuclear fusion ignites at the center and a new star turns on. Do this thousands of times within the same cloud over a few 100,000 years, and you get a cluster, hundreds or thousands of newborn stars still embedded in the gas that made them, gravitationally bound together by the sheer mass of that leftover material. Now add the massive ones. Stars like the future Alnitak, the future Alnilam, the future Mintaka. They ignite fast, and they ignite hot, and almost immediately they start fighting back against the cloud that made them. Watch it happen in sequence. A handful of the newborn stars cross a mass threshold and start pouring out ultraviolet radiation. The radiation strips electrons off the surrounding hydrogen. Stripped gas heats sharply and starts to expand. Expanding gas collides with stellar winds already tearing outward at thousands of kilometers a second. Meanwhile, the cluster's total gravity depends entirely on that gas being there. It stops being there within a few million years. A geological instant. Most of the cloud's original mass has been blown clean out of the system. That gas wasn't decoration. It was most of the mass. Strip it away fast enough, and the cluster's own stars are suddenly moving too quickly for what little gravity remains to hold onto them. The bound structure doesn't slowly loosen, it comes apart relatively quickly, stars flying outward on whatever trajectory they happen to have at the moment. The glue disappeared, a process, astronomers, with a certain dry humor sometimes call infant mortality. The name isn't an exaggeration. Studies of young star clusters across the galaxy suggest a large majority never survive this exact phase intact. Most newborn clusters lose enough mass, this fast, that they never become the kind of long-lived, gravitationally bound structure a cluster like the Pleiades represents. Surviving as a bound family, still orbiting a shared center billions of years later, is closer to the exception than the rule. Coming apart, the way the belt stars did, is closer to the default outcome of being born massive in the first place, which means the belt, in its own quiet way, is an ordinary story wearing an unusual disguise. Three unremarkable survivors of a very common kind of family collapse, dressed up by distance and coincidence into something that looks, from Earth, like deliberate design. The three belt stars are three survivors of exactly that event, scattered onto three different trajectories by the same sudden unraveling at the same rough moment from the same collapsing cloud. They didn't drift apart out of indifference. They were blown apart, together, by their own family's collective violence. Sit with that for a moment, because it reframes almost everything covered tonight. The three stars sharing this accidental line are not simply unrelated objects that happen to align. They are related genuinely, chemically, historically, and the very forces that made them siblings are the same forces that guaranteed they wouldn't stay together. That is not a metaphor being forced onto the data. It's the data. Stars born in the same cluster carry near-identical chemical fingerprints because they condensed from the same well-mixed cloud of gas at the same time. The same ratios of heavy elements, seeded by the same earlier generations of stars that lived and died before this cloud ever existed. Spectra taken of Alnitak, Alnilam, and Mintaka's components show exactly that kind of shared signature, the fingerprint of common origin, even as their measured distances from Earth disagree by hundreds of light years, and their true motions point in different directions across the sky, which leaves an uncomfortable, genuinely unresolved question sitting at the center of tonight's entire premise. And it will not be tidily answered before the credits. If two things share an origin, share a chemistry, share a birth event, but no longer share space, no longer share a path, no longer share anything a gravitational equation would recognize as a bond, are they still, in any meaningful sense, one family? Astronomy has an answer for the physics. It has no answer for the word. That question was never going to resolve cleanly tonight. And it isn't going to now. What the physics does offer, instead of an answer, is a reframing worth carrying forward. The line was never the connection. The line was only ever the coincidence. The connection, such as it is, was there before the line existed and will still be true long after the last human eye traces that line across the sky for the final time. Hold both of those facts at once, because the rest of tonight depends on not collapsing them into one simpler idea. The 3-star line is fake, an accident of standing in one particular place, at one particular moment, nothing more. And the kinship underneath it is real. Chemical, historical, older than the line itself, indifferent to whether anyone on Earth ever noticed it. Neither fact cancels the other. They are simply true at the same time, describing two completely different kinds of relationship hiding behind one single, familiar shape in the sky. That doubling one true thing sitting directly on top of another, contradictory true thing turns out to be the actual shape of almost everything covered tonight, once you look closely enough. 3 stars, not a line, but a lineage. One point of light, hiding a number that depends entirely on how strict you're willing to be about the word counts. Certainty, it turns out, was never really the point of tonight, and it may never have been the point of looking up at all. Here's a layer of the illusion tonight hasn't touched yet, and it might be the strangest one, because it has nothing to do with distance in space at all. It has to do with distance in time. Light isn't instantaneous. It crosses the gap between a star and your eye at a fixed, finite speed, which means every star you've ever looked at, you were never actually seeing as it is right now. You were seeing it as it was however many years ago the light needed to make the crossing. For Mintaka, that gap is roughly 1200 years. For Alnitak, close to 1300. For Alnilam, depending on which distance estimate you trust, somewhere between 1300 and 2000, which means the 3 points of light forming that single straight line were never even simultaneous. You're not looking at 3 stars as they exist in one shared present moment. You're looking at 3 completely different slices of the past, layered on top of each other. By coincidence, arriving at your eye in the same instant purely because each one happened to leave its source at a different point in history, calibrated to land here together, tonight. Now put a number on that gap, 1 star at a time. 1200 years ago, when the light currently leaving Mintaka began its journey, the events historians associate with the fall of the Western Roman Empire had already receded into the past by centuries. 1300 years ago, when Alnitak's current light departed, more than a millennium still separated that moment from the night. Deslandres pointed a spectrograph at an entirely different star in the same belt and started this whole story by accident. Nobody alive at that moment could have imagined a satellite, a spectrograph, or a species capable of reconstructing 5 hidden companions from nothing but the wobble in a beam of light. That light left before almost every institution currently studying it existed, before most of the languages spoken on Earth today had taken their current form. It arrived tonight anyway, indifferent to how long the trip took, indifferent to what changed on the small planet waiting to receive it. Consider what that means for your own eyes tonight. Sitting exactly where you are, every glance upward stitches together light that left its source at wildly different points in history, arriving together purely by coincidence of travel time, then departing again from your retina as a single unified impression. One belt, one moment, one glance. Your eyes were never built to notice the seam. They flatten arrival into simultaneity automatically, every single time, for every star in every sky you have ever looked at. So the belt isn't only a spatial illusion, 3 unconnected depths flattened into a false line. It's a temporal one too. 3 unconnected moments in history, flattened into a single false instant. Neither the space nor the time was ever real. Only the arrival, tonight, right now, was ever true. Mintaka is not some singular oddity, a once-in-the-sky exception to how stars normally behave. It's closer to the rule than the exception. And once you know to look, the pattern shows up everywhere overhead. Take Algol in the constellation Perseus, a star whose name descends from Arabic folklore, associating it with a ghoulish, demonic presence, likely because ancient skywatchers noticed something genuinely unsettling about it. Its brightness visibly dims every few days, dropping by more than half for several hours before recovering. Centuries before anyone understood why, people had already flagged this star as behaving wrongly. The actual mechanism, confirmed by astronomers in the 19th century, is exactly the trick powering Mintaka's inner pair. An eclipsing binary, one star passing in front of the other on a repeating schedule, dimming the combined light every time. Algol's rhythm repeats roughly every 2.5 days, fast enough that a patient, dedicated skywatcher without any instrument at all could, in principle, notice the dimming across a single long night, which may be exactly what happened long before anyone had a name for the mechanism doing it, or the mathematics to explain why a star would ever behave that way at all. Or take Mizar, the star at the bend in the Big Dipper's handle, one of the first double stars ever confirmed telescopically, back in the 17th century, and visible even to sharp naked eyes as two separate points if you know where to look. Modern instruments pushed the count further. Mizar itself turned out to be a close pair of stars, and its visual companion turned out to be a close pair as well. 4 stars total, hiding inside what early observers already knew wasn't quite one point of light, discovered in stages exactly the way Mintaka's family was, spread out across centuries of steadily improving instruments. The pattern holding all of this together is simple and worth saying plainly. The naked eye is a low-resolution instrument, built for survival on one particular planet, not for accurately counting stars. Every single star you've ever pointed at without a telescope is a claim made under those specific limits. A claim the universe has broken. Quietly and repeatedly, every single time anyone has bothered to check closely enough. The scale of that undercount, once astronomers went looking systematically, turned out to be enormous. Among the hottest, most massive class of stars. The same class every belt star and every component described tonight belongs to. Most were eventually found to have at least one close companion, not a rare configuration reserved for a small handful of interesting exceptions, but the ordinary condition, the one that needs no special explanation at all. A single, unaccompanied massive star floating through space with no companion of any kind is, if anything, the unusual case that needs explaining, which is exactly the open question tonight left sitting, unresolved, beside the middle star of this very belt. Return, for a moment, to the corridor from earlier tonight, the image of the belt as 3 walls stacked at wildly different depths, aligned only because of exactly where you happen to be standing. It's worth finishing that thought now, with everything else you know layered on top of it. Imagine an observer standing on a hypothetical world orbiting Alnilam itself, rather than the Sunday. From there, Mintaka and Alnitak wouldn't sit anywhere near each other in the sky. They'd scatter to opposite, unrelated points, mixed in among thousands of other unfamiliar stars, with no reason for anyone on that world to ever group them into a single shape, let alone give that shape a name and build a hunter's silhouette around it. The belt would not exist, not faintly, not approximately. It is a pattern that requires this exact vantage point, and nowhere else in the galaxy does that vantage point repeat. Push the thought experiment further still. Somewhere in this galaxy, right now, some other world is almost certainly orbiting some other star, and whatever beings or instruments exist there, if any do, are looking up at their own sky and tracing their own accidental shapes through their own unrelated points of light, each one a coincidence as convincing. From where they're standing, as this one is from here, every constellation in every sky is a local story. None of them travel. That is the final layer of the illusion. Underneath the depth and underneath the time, the shape itself is not a property of the stars. It is a property of the specific, tiny, almost absurdly narrow point in space where a human eye happens to be standing when it looks up. Move that eye far enough, and the shape simply stops being true. Not obscured, not distorted, just gone, replaced by whatever pattern that new vantage point happens to draw through an entirely different, equally accidental set of unrelated points of light. Trace the whole descent tonight has walked. One more time, from the widest scale down to the narrowest. It started with hundreds of light years separating 3 stars along a line only Earth can see. It narrowed to a fraction of an arc-second, separating 5 points of light crammed into one unresolved star. And it ends here, at a single vantage point no wider than the space between 2 human eyes. The actual, physical location required for any of tonight's illusions to hold together at all, which means every constellation you have ever learned, every shape you have ever traced across a night sky anywhere on Earth, shares that exact same fragile status. Not evidence of design, not a message written into the stars. A momentary, local coincidence of geometry. True here, true now, true for as long as you happen to be standing in this one specific place in the universe, and true for nobody, anywhere else, ever again. Babylon wasn't the only civilization to notice this line and build meaning around it. Almost everywhere humans have kept careful records of the sky. This exact coincidence of geometry shows up under a different name, attached to a different story, each one convinced it was seeing something coherent. Ancient Chinese astronomers folded the belt into a much larger asterism called Shen, one of the 28 lunar mansions used to track the moon's monthly path against the background stars. A system that had been refined and maintained by court astronomers for well over 2,000 years, entirely independent of anything happening in Babylon or Greece. Norse tradition told a different story about the same 3 points, describing them as the spindle of the goddess Frigg, spinning thread across the winter sky. In ancient Egyptian tradition, the constellation was linked to Sa, a sky god associated with Osiris, a genuine, well-documented piece of Egyptian religious astronomy, distinct from the far shakier modern claims sometimes made about pyramids and star alignments, which most serious archaeoastronomers treat with open skepticism. 3 completely different cultures, 3 completely different stories, built on top of the exact same accidental alignment, a coincidence of geometry so visually convincing that it independently persuaded observers, separated by oceans and thousands of years, that they were looking at something meaningful, something worth building a myth around. None of those cultures were wrong to notice the pattern. The pattern is real, in the narrow sense that it's genuinely there, genuinely visible, genuinely useful for marking a season or a heading. What none of them could have known is that the object producing that pattern wasn't an object at all, just 3 unrelated stars, sharing nothing but a fluke of shared direction from one small, specific vantage point in the galaxy. What's worth noticing is how little the specific story mattered compared to the shape itself. A goddess's spinning tool, a hunter's belt, a sky god's household, 4 wildly different narrative frameworks imposed by cultures with no contact and no shared language, all reaching for the same 3 points of light because the points of light themselves practically demanded a story. The geometry did the persuading. The mythology just supplied the words. That's a pattern worth remembering for the rest of tonight, because it's about to repeat at a much larger scale. A hidden order that turns out to be less about the object and more about whatever a given observer happens to bring to it. None of these traditions were in contact with each other when they built their versions of this story. Babylon, China, Scandinavia, and Egypt developed independently, separated by mountains, oceans, and centuries, with no shared texts and no shared teachers, and yet each one landed on the same underlying instinct. 3 bright points in a row, close enough together to feel deliberate, deserve a name and a story. That convergence says less about any single culture's insight, and more about a universal feature of the human eye encountering this exact, accidental geometry. proof that the illusion was strong enough to fool every observing tradition equally, everywhere it was ever seen. Here's the part worth sitting with. Rather than rushing past, none of those ancient observers were foolish for building meaning around an illusion. They didn't have the instruments to know it was one, and even now, knowing exactly what it is, the pull to see a shape up there hasn't gone away. You still see the line. You still see the hunter. Tonight's entire hour of careful measurement hasn't erased that impression from your own eyes, and it won't. That's worth noticing, because it says something about how human attention actually works, not about a flaw in it. Brains are built to find pattern first and question it second, if ever, a shortcut that has kept the species alive far longer than it's occasionally embarrassed it. Seeing a hunter's belt in 3 unrelated stars costs nothing and occasionally helps you find your way home across an unfamiliar sea. The instinct isn't broken. It's simply not built for the kind of precision this belt has spent tonight quietly failing to have, which leaves an honest, slightly uncomfortable question standing in the middle of the room. If the shape was never physically real, was the meaning people built on top of it ever real either? Every calendar set by this line, every voyage steered by it, every myth told beneath it, actually happened. Actual human lives were shaped by an object that never existed as one thing. The meaning was real, the object underneath it was not. Both of those statements are true at the same time, and neither one cancels the other. There's a version of this that could read as a small tragedy, centuries of navigation and myth, quietly resting on a foundation that was never there. That's not the only way to read it, and it may not even be the most honest way. The line gave people something they genuinely needed. An anchor point, a shared reference, a piece of the sky reliable enough to trust with a season's harvest, or a ship full of lives. It did that job completely, for thousands of years, regardless of whether the 3 points behind it ever agreed to be one thing. Usefulness and truth turned out to be 2 separate questions the whole time, and almost nobody, for almost all of human history, had any reason to notice they'd been quietly answering only one of them. You don't need the belt to be one object for it to have done its job. A calendar doesn't require its markers to be physically connected. It only requires them to hold still long enough and reappear reliably enough for a pattern of behavior to form around them. Every culture covered tonight built something real and lasting on top of a coincidence, and none of it collapses now that the coincidence has a name. If anything, knowing the truth adds a layer the myths never had access to. Not just a story about a hunter or a goddess, but a story about how far 3 unrelated points of light can travel before landing together. In one small human eye. Here's where tonight's story stops being purely historical and becomes something you could actually go and verify yourself on a clear night without needing a research-grade instrument. Mintaka's third component, the subgiant Heinz first proposed in 1980, later confirmed by speckle interferometry, and Hipparcos sits close enough and bright enough relative to its parent that a well-made backyard telescope under steady atmospheric conditions has a real chance of separating it from the primary's glare. It won't be dramatic. It will look like a faint point clinging stubbornly close to a much brighter one, easy to miss, easy to dismiss as an imaging artifact if you don't already know to look for it. But it's really there, doing exactly what a piece of hard-won 20th century astrometry says it's doing. Mizar, meanwhile, is one of the most forgiving double stars in the entire sky for a first-time observer. A modest telescope, even a fairly small one, splits it cleanly into 2 separate points of light on almost any clear night. No advanced technique required. It's often the very first real double star an amateur astronomer ever resolves, precisely because 17th century observers found it exactly the same way, with instruments far cruder than what most backyards now casually own. None of this requires travel, or luck, or specialized access. It requires clear sky, patience, and the willingness to point an ordinary instrument at a familiar shape and watch part of its accepted simplicity quietly fall apart in real time, the same way it fell apart for every astronomer named tonight. one measurement at a time. Alnitak's inner pair, by contrast, will never split apart in an ordinary backyard eyepiece. No matter how good the night, or how large the amateur mirror, the two stars sit too close together at too great a distance for a conventional telescope to separate them directly. Splitting that particular pair takes interferometry, combining light from multiple separated telescopes to synthesize the resolving power of one impossibly large mirror, a technique currently confined to a handful of professional research facilities. Some parts of this belt's hidden structure are available to anyone patient enough to look. Others are available only to instruments built specifically and expensively for exactly that purpose. There's a rough hierarchy hiding inside that difference. Worth carrying forward, the easiest secrets go first, found earliest, confirmed with the simplest tools. The hardest secrets go last, and some of them may never fully resolve, not because nobody's looking, but because the physics itself sets a limit on how finely any instrument can ever divide one point of light into its true components. Mintaka's outer two companions, still not fully confirmed as bound members of the family, sit somewhere in that harder category. Plausible, likely, and still waiting. The same way the third star waited 19 years between a claim and its proof, patiently, in plain sight, the entire time. Alnilam isn't the only belt star with a violent, largely settled future. Alnitak's primary, at roughly 28 times the Sun's mass, is heavy enough to be walking the exact same road. Hydrogen giving way to helium giving way to heavier elements, each stage faster and hungrier than the last, ending, eventually, at an iron core that can no longer hold itself up. The timeline is less tightly pinned down than Alnilam's, partly because Alnitak's mass estimate carries its own uncertainty, and partly because a star, this complicated, magnetic, in a close binary, quietly losing material to a wind its own field is actively shaping, resists the kind of clean modelling a simpler, solitary star allows. What's not in serious doubt is the outcome. Somewhere in the next several 100,000 to roughly 1 million years, on a timeline broadly similar to its unaccompanied neighbour, Alnitak's primary reaches the same iron wall, collapses and lights up briefly bright enough to be seen from the far side of the galaxy, outshining every other star in its home system for a span of days. 2 of the belt's 3 stars, in other words, are already on a converging path toward the same violent kind of ending, on roughly overlapping timelines, for the same underlying reason. Mass this large simply does not get to choose a slower, quieter death. Here's the detail that makes Alnitak's ending stranger than Alnilam's. It isn't going alone. Whatever happens to the primary happens to a star locked in a 7-year orbital dance with a smaller companion and to a magnetic field currently shaping the wind of both. A collapse that dramatic doesn't quietly end one star and leave its neighbours untouched. The explosion would blast the region with radiation and debris intense enough to disrupt the close companion's outer layers, and possibly strip material from it directly. An ending that takes at least 2 stars down with it, not one, the moment the core finally gives out. And the third star, orbiting from 1,500 years out, would likely survive relatively unscathed, watching the collapse of its 2 inner companions from a safe enough distance to keep going largely unaffected, then aging alone, the last surviving witness of the system it was born into. There's something worth sitting with in that asymmetry. 3 stars, born together, bound together, for however many centuries their shared orbit lasts. And when the ending finally arrives, it doesn't arrive for all 3 at once. 2 go down together, caught in the same catastrophic instant. One simply keeps going, carrying whatever's left of the family's shared history forward alone, into a future none of tonight's measurements can fully predict. Endings, even for stars born from the exact same event, are rarely distributed evenly, and the survivor, whenever its own turn eventually comes, will face it alone, with no siblings left nearby to share the sky. Mintaka's inner pair faces an entirely different kind of ending. One that has nothing to do with waiting quietly for an iron core to form. Two massive stars orbiting this close together, completing a lap in under 6 days, are not gravitationally stable forever in their current configuration. As the larger of the two continues burning through its fuel, it will swell. Stars generally expand as they age, sometimes dramatically, in the later stages of their evolution. And a star swelling inside an orbit this tight runs into a hard physical limit fairly fast. On stellar timescales, at some point, the expanding star's outer layers can cross into the region where the companion's gravity dominates instead of its own. The material starts spilling directly from one star onto the other. That process, called mass transfer, can end a few different ways depending on exactly how much material moves and how fast, and it's a common enough pathway for tightly orbiting massive pairs that astronomers have built entire subfields of stellar physics around cataloguing and modelling the different possible outcomes. Sometimes it settles into a new, stable configuration, with one star fattened by the transfer and the other stripped down to a smaller, lighter remnant of its former self. Sometimes the transfer becomes unstable, spiraling the two stars closer together until they touch and merge outright into a single, more massive star. A stellar collision playing out in slow motion over years or decades rather than seconds, driven by orbital mechanics rather than a direct, sudden impact. Nobody can say with certainty, tonight, exactly which version of that ending Mintaka's inner pair is heading toward, or precisely on what timeline that future arrives. What's already clear from the physical setup, the separation, the masses, the speed they're aging at, is that stay exactly as they are, indefinitely, is not one of the available outcomes. The tightest, most extreme orbit in the entire five-star system is also the least stable one, already carrying the seeds of its own eventual transformation, encoded in the same tight geometry that made it discoverable in the first place. There's a strange kind of symmetry hiding in that fact, worth pausing on before moving forward. The exact closeness that let Deslandres catch a velocity signal in 1900, that let later astronomers measure an eclipse precise enough to reconstruct both stars' masses, is the same closeness now steering the pair toward eventual merger or transformation. The property that made this system discoverable and the property that makes it unstable are not two separate facts about Mintaka's inner pair. They are the same fact, viewed from two different points in time, one from the astronomer's side of the telescope, one from the star's own slow, physical future. Two vantage points that happen, in this one particular case, to be describing the exact same narrow gap of space separating two orbiting stars. Zoom out from individual stars, and the same pattern that hid 4 extra companions inside Mintaka turns out to repeat at nearly every scale astronomers have learned to examine closely, objects once catalogued as single, fuzzy patches of light. Nebulae, as 18th and 19th century observers called anything diffuse and unresolved, turned out, once telescopes improved, to be entire, separate galaxies, each containing hundreds of billions of stars, sitting at distances so extreme that no instrument of the time could resolve individual points of light within them. What looked like one small smudge was, and always had been, an entire galaxy's worth of hidden structure, waiting on better resolution to be believed. Individual stars have suffered the same fate, over and over, at every scale in between, and not always because the technology needed centuries to catch up. Sometimes it simply took someone deciding to look harder at data that had been sitting, unquestioned, in an archive for years. Planets orbiting distant stars were, for centuries, undetectable in principle. A star's light is so overwhelming compared to any orbiting planet's reflected glow that direct viewing was effectively impossible with the tools available. The same indirect logic that caught Mintaka's inner pair, a rhythmic wobble in a star's light. Too small to see, large enough to measure. is now the primary method used to confirm thousands of planets orbiting other stars, planets that would otherwise remain permanently invisible, folded into what looks, from Earth, like one undisturbed point of light. The lesson repeating across every one of these examples is the same lesson Mintaka has spent tonight demonstrating in miniature. Resolution is never really about the object being examined. It's about the limits of whoever, or whatever, happens to be doing the looking. Raise the resolution, and singular things keep turning out to be plural, not occasionally, not as some rare exception worth remarking on, but reliably enough that the honest working assumption, at this point, should probably run the other way. Assume hidden structure until proven otherwise, not the reverse. Sit with how far that idea actually reaches. Once you let it, every unresolved smudge a large enough telescope has ever photographed, every star too faint or too distant to split into its true components, every single point of light currently sitting in any catalogue anywhere is a candidate for exactly the kind of quiet correction Mintaka has already received twice, once in 1904, once in 1999, and possibly, if the outer two components ever get their proof, a third time still to come. The sky isn't full of finished answers. It's full of points of light, still waiting for someone patient enough to ask the same question Deslandres asked. By accident. In the first year of the 20th century, a question that took nearly 100 years, 4 separate methods, and 2 astronomers willing to distrust a comfortable number to finally answer in full. Every confirmed piece of Mintaka's hidden structure tonight was found the same basic way. A claim, treated with appropriate suspicion, sitting unresolved for years or decades, until a new instrument or a new analysis finally settled it one way or the other. The outer 2 components, the ones this episode has been careful and honest about not fully confirming, are sitting in exactly that same holding pattern right now. Tonight, while you listen, modern astrometry is closing that gap faster than any single technique available in 1980 or even 1999 could have managed, and it's doing it for hundreds of thousands of ambiguous systems at once. Space-based missions built to measure stellar positions and motions with extraordinary precision have been steadily producing exactly the kind of long baseline proper motion data that settles questions like this, not through a single dramatic image, but through years of patient, repeated measurement. The same unglamorous process Deslandres and Hartmann were already practicing more than a century ago, with far cruder tools on a single star, one careful night at a time. If the outer 2 components genuinely share Mintaka's motion through space, moving together across decades of careful tracking, that shared motion will eventually show up clearly enough in the data to end the argument for good. If they don't, the data will show that too, just as plainly, whichever way it happens to land. Nobody watching tonight, and no scientist currently working the problem, gets to skip that waiting period, no matter how badly either side wants an answer sooner. That's not a flaw in the process. It's the same discipline that turned a wrong 2-day guess into a confirmed 5-day truth, that turned an unconfirmed 1980 proposal into an accepted 1999 discovery. The pattern holding this whole episode together. Claim, doubt, patient measurement, eventual resolution, isn't finished with Mintaka. It's simply paused at the point current instruments have managed to reach, waiting for the next data set, the next careful reanalysis, the next astronomer willing to spend years chasing a number that doesn't quite fit. That's worth remembering the next time a documentary, or a headline, or a confident voice states a fact about the universe as if it arrived complete and finished. Almost nothing does. Every settled number tonight has covered the 5.7-day orbit, the 2,687-day period, the roughly 1,200 light-years, passed through exactly this same holding pattern first. Proposed, doubted, checked, rechecked, and only then allowed to graduate into the kind of fact a narrator can state plainly without hedging. The outer two components of Mintaka aren't an exception to how astronomy works. They're a rare chance to watch the ordinary process happen in real time, before the answer has fully arrived, rather than being handed the finished result and never seeing the years of doubt it took to get there. Here's a layer beneath everything covered tonight that rarely gets said out loud. The word star, on its own, turns out to be far less precise than it sounds, even before you start counting how many of them are hiding behind a single point of light. Some close binary pairs orbit so tightly that their outer layers physically touch and share a single, merged envelope of gas. Objects astronomers classify as contact binaries, where drawing a clean boundary between star 1 and star 2 stops being a simple geometric question and becomes a genuinely difficult one, because the material itself doesn't respect the line. Other systems pass through phases of active mass transfer, material actively flowing from one star to another, blurring not just where one star ends and another begins, but which star even owns which atoms at any given moment. The same process this episode already described happening, eventually, to Mintaka's own inner pair. None of the belt's known components have reached that particular extreme yet. Mintaka's inner pair is close, tightly orbiting, genuinely unstable in the long run, but not yet merged or touching. Still, the existence of stars that blur past even that boundary is worth holding on to carefully, because it completes the larger argument this whole episode has been quietly building toward. One star was never as simple a category as a single glance upward suggests. Sometimes the difficulty is resolution. 5 points of light too close together for any instrument to separate. Sometimes the difficulty is definition itself. Material shared between two stars so thoroughly that the very idea of drawing a clean boundary between them stops making clean physical sense at all. Both problems point at the same underlying truth. The tidy, singular category star, like the tidy, singular category belt, turns out to be a convenience built for a human eye working at human resolution. Useful, load-bearing, genuinely functional for almost every purpose it's ever been asked to serve, and not, underneath that convenience. None of this is a criticism of the word, and it isn't a reason to throw the category out. Categories exist to be useful, not to be perfectly precise, and STAR has done its job well enough to carry human astronomy from the first naked-eye catalogues all the way to interferometers, capable of resolving orbits invisible to the very founders of the field. But every category built for convenience eventually meets an edge case that exposes the convenience for what it is. A simplification, not a law of nature. Contact binaries are one such edge case. A 5-star system hiding behind one unresolved point of light, patiently uncounted for most of a century, is another. The word survives both, and will likely survive whatever comes next too. It just survives them a little less confidently than it did before tonight began. Every discovery tonight has covered shares. One detail rarely stated outright. None of it happened because the universe was ready to be understood. Mintaka's inner pair was eclipsing itself every 5.7 days for millions of years before Henri Deslandres ever pointed a spectrograph at it in 1900. The third companion sat exactly where Wolf Heinz eventually found it for just as long before 1980, indifferent to whether any instrument on Earth was pointed its way. Nothing about the timing of these discoveries was written into the stars themselves. The stars simply kept doing what they were already doing, on schedules set by gravity and fusion, entirely unconcerned with whether anyone was watching. That's a harder kind of indifference to sit with than the more familiar version. The vastness, the cold, the empty distance between one star and the next. This is smaller and closer than that, and somehow more unsettling for it. The universe was never withholding this information, the way a puzzle withholds its solution until you look hard enough. It simply had no relationship to being known at all. The 5-star structure hiding inside Mintaka wasn't a secret. A secret implies someone keeping it. This was simply true the entire time, with or without a single observer capable of noticing, which means every discovery covered tonight was never really about the universe revealing something. It was about human instruments, human patience, and human doubt finally catching up to a truth that had been sitting there, complete and unconcerned, the whole time. The stars did not wait for Deslandres. They did not wait for Heinz, or for Mason's team in 1999, or for the Hipparcos satellite quietly gathering astrometric data in the background of an unrelated mission. They were simply going to keep doing exactly what they were doing, discovered or not, noticed or not, for as long as fusion keeps them burning. That's not a comforting thought. And it isn't meant to be one. It's the specific, quiet kind of awe this particular fact deserves. Not a universe hiding secrets from you, but a universe that was never organized around you, learning them at all. And somehow, underneath that indifference, the secrets got found anyway. That last part is worth holding on to a little longer than the indifference itself. Indifference alone is an old idea, familiar from 100 other documentaries, about 100 other cold, uncaring cosmic facts. What's less often said is what sits on the other side of that indifference. A small, stubborn, entirely human habit of looking anyway, measuring anyway, doubting a comfortable number anyway, for no reason the universe ever asked for or rewarded. Mintaka didn't care whether Deslandres kept measuring. He kept measuring regardless. That gap between a universe that owes nothing and a species that keeps looking regardless, for no reward beyond the looking, itself is where every single fact in this episode actually came from. Everything covered tonight is, in principle, available to you directly. Not as an abstraction viewed from a screen, but as 3 actual, physical points of light you can walk outside and locate, on the right night, in the right season, with nothing more than a clear sky and a little patience. Orion climbs highest in evening skies across the late months of the year, the belt itself unmistakable once you know to look for it. 3 stars of nearly equal brightness, evenly spaced, tilted at a recognizable slant, sitting almost exactly on the celestial equator, which is part of why it's visible from nearly anywhere on Earth, north or south, unlike constellations confined to one hemisphere's sky. Find that slanted row of 3, and you've found, with your own unaided eyes, the exact illusion this entire episode has spent its runtime taking apart. The same 3 points of light Babylonian skywatchers once catalogued, still hanging in the exact same familiar shape. From there, the deeper layers open up in stages, matched almost exactly to the order tonight uncovered them. Binoculars, held steady, start to hint at texture around the eastern star that a naked eye reads as a clean point. A modest telescope, under a dark and steady sky, has a real chance at splitting Mintaka's third companion from its brighter neighbor. Faint, close, and easy to miss, but genuinely there, exactly where a century of careful measurement says it should be. None of this requires travel, or rare weather, or specialized access. It requires the same 3 ingredients every discovery tonight eventually depended on: a clear enough view, an instrument matched to the question, and enough patience to keep looking instead of assuming the first glance already told you everything there was to know. You don't have to do any of that tonight. The permission to simply listen, eyes closed, letting the description stand in for the sky, is exactly as valid as pointing a telescope at it yourself. But the option is there. Waiting the same patient way Mintaka's hidden companions waited, not going anywhere, not needing anyone in particular, available exactly as it's always been to whoever eventually looks. There's a particular kind of satisfaction in that availability, worth naming before tonight moves on. Nothing about tonight's story required a research budget, a satellite, or a career in astrophysics to verify for yourself, at least in part. The same sky Deslandres measured from a Paris rooftop in 1900 is still up there, unchanged in any way that matters to a human eye, waiting on the same patient looking that cracked it open the first time. The instruments have improved almost beyond recognition. The belt itself, and the quiet invitation it extends to anyone willing to look closely enough, have not changed at all. Everything tonight has circled back, again and again, to a single number. 3 stars, or 1 star, or 5 stars, or 4 companions, or 2 eclipsing points of light on a 5-day rhythm. It would be easy to walk away from all of that thinking the whole episode was an exercise in counting. Getting the tally right, correcting old mistakes, landing on the true, final number where earlier generations landed on the wrong one. That was never actually the point. And it's worth reorganizing everything you've heard around the real one before tonight moves any further. The number was never the lesson. The lesson was what it took to get any number at all. How much doubt, how much patient rechecking, how many decades of a claim sitting unconfirmed before anyone was willing to call it true. Deslandres' mistake wasn't a failure of counting. It was a completely reasonable first estimate, built on real data, corrected only because someone else cared enough to keep measuring after the first answer arrived. Heinz's proposed companion wasn't wrong for sitting unconfirmed for 19 years. Unconfirmed was the honest, appropriate status for a claim that hadn't yet met its burden of proof. Even the belt's outer 2 components, still not fully settled tonight, aren't a loose thread this episode failed to tie off. They're a live demonstration of the same discipline that resolved everything else, simply caught mid-process instead of after the fact, which means the actual through line connecting a 3,000-year-old Babylonian star catalogue to a 1999 speckle interferometry paper isn't how many stars are really there. It's how much confidence does any single glance upward actually deserve. 3 stars looked like 1 line. 1 point of light looked like 1 star. A shared birth cloud looked, for a while, like a shared destiny. Every single mistake tonight corrected was the same mistake, wearing a different disguise, treating the resolution available to one particular observer at one particular moment as if it were the whole truth, rather than the limit of what that observer happened to be equipped to see. That reframing doesn't make the individual facts less true. Mintaka really does hide 5 points of light. The belt really is an accident of geometry. But underneath both of those facts sits a bigger one, the one this entire hour has actually been building toward without saying it directly until now. Certainty was never something the universe owed you. It was always something you had to go and earn, one patient measurement at a time. The same way every single astronomer named tonight eventually did. That's a harder lesson than 1 star turned out to be 5. And it's the one worth actually carrying out of this episode. Facts arrive cheaply now. A headline, a caption, a single confident sentence delivered without any of the decades of doubt that had to happen first. Tonight tried to do the opposite, to show the doubt as clearly as the discovery, to let a wrong guess sit on screen for exactly as long as it took real astronomers to notice it was wrong. The number 5 is worth remembering. The century it took to earn that number, honestly, might be worth remembering more. There is one thread from earlier tonight this episode is not going to tie off. And it isn't an oversight. It's a genuine, open tension. And pretending otherwise would be a smaller kind of lie than the one about the line itself. 3 stars were born together, from the same collapsing cloud, at the same rough moment, and were then blown apart by the very violence of their own birth, never to share space again. It is the literal, physical history of the belt overhead right now, and it leaves an honest question sitting in the room that no amount of additional data will ever fully settle. Does sharing an origin, without ever again sharing a path, count as belonging to each other? Human language has words for family that requires proximity, and words for family that survives distance across a single lifetime. But nothing quite built for a kinship this old, this thorough, and this permanently, irreversibly, unrecoverably scattered. Tonight is not going to pick a side. It would be easy to reach for comfort here. To say the shared origin is enough, that distance never really mattered. That the three stars remain a family in every sense that counts. It would be just as easy to reach for the colder version, that a birth event millions of years in the past means nothing once the last gravitational bond has broken. That related without connected is just a story told after the fact. Both of those framings resolve the tension. Neither of them is more honest than simply leaving it open. So this is where tonight sits inside it. Instead of resolving it, the three belt stars are, at the exact same time, absolute strangers occupying no shared space, moving on no shared path, bound by no shared force, and siblings, in the fullest chemical and historical sense that word can carry, products of one single collapsing cloud that no longer exists in any form. Both descriptions are completely accurate. Whether that makes them, in any sense that matters, still family. That is a question tonight is going to leave exactly where it found it. Open, unresolved, and entirely yours to sit inside for as long as you'd like. There is no third measurement coming to settle this one. The way a fourth technique eventually settled Mintaka's third star. This isn't a gap in the data, it's a gap in the language. And language doesn't resolve the way an orbit does. Whatever answer you land on tonight, drifting towards sleep is not going to be wrong. It's simply going to be yours. Arrived at the same way every honest answer in this episode arrived. Slowly, without full certainty, and without anyone requiring you to be sure before you're allowed to rest on it. So, is Orion's belt an illusion? And is one of its stars actually 5? Both, and neither answer is the whole of it. And by now, you have enough of tonight's careful, patient measurements to hold the complete shape yourself. The 3-star line is an illusion, built from nothing but the accident of standing at one specific point in the galaxy, at one specific moment, while 3 unrelated giants happen to sit along the same sightline at wildly different depths. It is also, at the exact same time, a genuine record of kinship. 3 siblings from one collapsing cloud, scattered by their own violent birth, chemically bound to an origin no gravity holds together anymore. And the westernmost of those 3 stars really does hide 4 companions inside a single point of light. 3 of them proven beyond reasonable doubt across nearly a century of patient, skeptical measurement. 2 more, still waiting on the same discipline to finish its work: illusion, kinship, and multiplicity. 3 separate true things, stacked inside one shape, none of them cancelling the others out. Add the 4th layer tonight, uncovered almost by accident. Even the moment of seeing that shape is an illusion in its own right. 3 unrelated slivers of the past. A Roman-era light, a slightly younger light, a light older or younger still, depending on which distance estimate eventually wins, arriving together only because of how long each one happened to spend crossing the dark. A star was never really the right unit to measure any of this by. A star is just the smallest thing a naked eye can resolve on its own. The flaw of human vision, not a fact about how the universe organizes itself. Raise the resolution even slightly, in any direction tonight has pointed, and the flaw gives way to something more crowded, more layered, and more honestly complicated than a single point of light was ever built to represent. Which brings tonight back, one final time, to where it started. 3 stars, spaced almost perfectly even, hanging in a straight line above the horizon. And underneath that simple, familiar shape, 3 stars that have never once agreed to be a line, and one of them that never agreed to be one star at all. That is not a mystery left dangling. It is the actual, complete answer, held all the way through instead of resolved too early. The kind of answer that only arrives after you stop needing the sky to be simpler than it is, and let it be exactly as layered, as patient, and as unfinished as everything else covered tonight. Somewhere past all three stars, past the drifting, past the 50,000 years still separating tonight's sky from whatever unfamiliar arrangement eventually replaces it, the same pattern is almost certainly waiting inside countless other points of light this episode never had time to reach. Other single stars quietly hiding second, third, fourth companions, other constellations built on coincidences no one has bothered to unravel yet. Tonight only had room for one. The sky, indifferent as always to how much of itself gets noticed, keeps the rest exactly where it's always kept them, hiding in plain sight, waiting on nothing but a patient enough measurement. We've drifted through a hallway of stars tonight. 3 walls stacked at 3 different depths, mistaken for one straight line by every eye that has ever looked up from this particular planet. We've watched a French astronomer's 5-day mistake become a 100-year truth, followed a magnetic field no massive star was supposed to keep, and stood beside a giant so restless it can't even agree with itself on how far away it stands. We've wandered all the way down to a single unresolved point of light and found 5 stars waiting inside it. Patient, unbothered, indifferent to the century it took anyone to notice. None of that distance was ever really between you and the stars. It was between one moment of not knowing and the next moment of knowing a little more, and that gap is the same gap every person who has ever looked up has stood inside, together, without quite realizing it was shared. The belt was never yours alone to wonder about. It never was anyone's alone. That's what our has meant. This whole time, if your eyes feel heavy, let them close. There's nothing left tonight that needs to be understood before you're allowed to rest. If this felt like home, leave a comment when you wake up. The universe will still be here when you wake up. So will we. Good night.